So we have been discussing interacting theory. And in the previous lecture, so in particular we are discussing lambda phi 4 theory in 0 plus 1 dimension. And in the previous lecture we found that due to the presence of interaction, there are now new vertices. There are now new rules, i.e., we need to consider internal vertices. Which are of the following form. I mean, basically in lambda phi 4 theory, and every such vertex in momentum space will come with a factor of this. And also okay. So let's now try to use these rules to compute various things. So let's now start with computation of 2-point function in frequency space. So the first contribution is of course this one, which is the contribution of free theory. Then since this is 2-point function, we can have two external point and any number of internal points. So then this contribution will be I by h bar omega square minus m square plus I epsilon whole square, and then this vertex that will come with minus I lambda over h bar, and then the frequency of that loop of that internal propagator is not determined by momentum conservation, so this will be d omega I by h bar omega, so let's call it d omega tilde squared minus m square plus I epsilon. So this is one, and then you can have two vertices, but there are two different ways to draw two vertices. One is this, and then second is of course this. Okay, so this contribution, this will be simply just like above, so IH d omega tilde IH bar over omega tilde square minus m square plus I epsilon, this whole square, and this will be then there will be two undetermined frequencies, so let's call them omega 1 and omega 2, d omega 1 d omega 2 I by h bar was omega plus omega 1 plus omega 2 whole square minus m square plus I epsilon. Okay, so all these integrals can be explicitly done, but at this point we introduced something called self energy diagram. So okay, so firstly these integrals can be explicitly done. Be careful with I epsilon. Also this integral can also be done. But important thing is that let's first introduce something called self energy diagram. So self energy diagram are diagram. So these are diagram with two external legs. And the second is that it cannot be cut into two pieces by disconnecting any one line. So for example, this is a self energy diagram. To be, when I am saying external leg, these are not, so this part, just this part is the part of the self energy diagram. So self energy diagram usually denoted by sigma. But for example, this is not a self energy diagram. Because I can disconnect it if I cut this line. If I cut this line, the diagram breaks into two pieces. But for example, there is another self energy diagram, which is, for example, we have drawn above. So this part, this is a self energy diagram. Okay. And bottom line is that, so the important part is that we have to first, so the structure of the 2-point function, so the structure of the 2-point function is that something like, so for example, self energy diagram in self energy diagram in lambda phi 4 theory is something like this, and then this, and then you can see that the correction to the 2-point function takes the following form. So firstly there is a self energy, there is this piece, and then I have this, which I denote as sigma, so which means it is some self energy diagram. Then I have this 2 self energy diagram plus dot dot dot, which means that it takes the from IH bar over omega square minus m square plus I epsilon, then in bracket 1 plus the self energy diagram over omega square minus m square plus I epsilon power n, where n run from 1 to infinity. Okay, so this is the structure of the 2-point function. And the interesting thing, useful thing is that in this case, then you can always resum it. So then this thing just becomes I by h bar omega square minus m square plus I epsilon, and this thing becomes just 1 minus this is same as, we can just multiply this two. Okay, and this is a very useful formula. So this formula is the structure of the 2-point function, analytic structure of the 2-point function. where sigma omega is the self energy diagram. So let's just do some computation. So actually the propagator, so also this is true, this is from Callahan-Lemon. So from Callahan-Lemon formula, the pole of the propagator tells about the spectrum. Okay, so let's just try to do one computation. So let's try to compute one loop self energy diagram. So in this case the self energy diagram was just this. You can do this computation. This will just become I lambda by 2 infinity to infinity minus infinity to plus infinity d omega by 2 pi I by omega square minus m square plus I epsilon, and this simply becomes I by lambda over 4m. Okay, so now if you put this in the above expression, then you can see that the structure of the propagator becomes I by h bar e square minus m square okay, and this quantity is called renormalized mass. So by definition mr square renormalized mass square is m square, I mean this is the one loop renormalized mass plus of course there will be order lambda correction, order lambda square correction. Okay, so the important thing is that note that h of mr minus m, if you compute this quantity, this will just become h bar square lambda over 8m square. Check. Okay, and this thing you can compare this with time independent perturbation theory. And you can check that this quantity is same as the first correction of the first excited level minus the first correction of the ground state level. Okay, we wrote down the expression before, if you remember. The expression for correction to the energy En1 minus E01, we wrote it in the previous lecture. This is lambda square over h bar square 16m square minus n square plus n. So put n equal to 1 and you get this expression. So we this is one explicit demonstration that we recovered result from time dependent. So we recover the time independent perturbation theory result from time dependent perturbation theory. Now let's just compute 4-point function. So for 4-point function, we just do in a diagrammatic way. So the first contribution will be of this form. So let's, of course, there is free theory result plus. So then there are contributions which are of this form. And this is, okay, let's just do this. And then we will have contribution. So this is one internal vertex. Now we are go to 2 internal vertex. Of course, there are also diagrams which are like this, or so let's write. So this is 1 2 3 4, 1 2 3 4. So firstly here we can consider 2 goes to 4 goes to 2, and we can also consider 4 goes to 3. And in this, here we can consider, so this is 1 2 3 4. So this is the self energy bubble. So self energy bubble at leg 1 or 2 or 3. Okay. So these are not genuine corrections to 4-point functions. These type of diagrams. So we focus on the other corrections. So if we focus on the other corrections, then how do they look? They look like there are 4 products of this, and then the first term is minus I lambda over h bar, right? Then the second term is minus I lambda over h bar square, and then it's a loop integral omega square minus m square plus epsilon times I by h bar omega plus omega 1 plus omega 2 square minus m square plus epsilon. And then of course, as we discussed there, sorry, this is 1 over 4. 4 goes to 2 and 4 goes to, and then there are also higher order corrections which are of the order I over h bar square cube something plus dot dot dot. So this is the way we compute perturbative correction to various correlation function by putting one or two or three numbers of internal vertices. Okay, so this is the way we will do the computation, and one can also analogously do computations in 3+1 dimension, which we will briefly discuss later. But one important point is that, again, symmetry and perturbation theory briefly mentioned. So here you see that the potential was lambda phi 4, so which means it has a Z2 symmetry. Okay, and one consequence is that any odd point correlation, any correlator with odd number of phi vanishes. I mean, this was true in free theory, and this is also true in perturbation theory. Since the perturbing potential obeys the symmetry. Okay, so this is a simple case of more general things, that whenever there are perturbing potentials which preserve some of the symmetries, then the various correlation functions, which are usually, this is the simplest case of what is known as word identity. So whenever the theory has a symmetry and the perturbing potential has a symmetry, then we will see that in the correlation function there are many correlation functions which just become zero because as a consequence of the symmetry. So we discussed a simple case of due to a Z2 symmetry. Later we will see more general scenarios, and in the next lecture we will discuss about, so this time we discussed about 0+1 dimension. In the next lecture we will discuss about 3+1 dimensions.